We grow up learning that stars are the engines of the universe, forging elements, warming planets, and marking the centers of solar systems across every galaxy. But what if I told you that the Milky Way is filled with a hidden population of cosmic objects that never got the chance to become stars at all? These are brown dwarfs, the quiet, dim, and often overlooked failed stars that drift through our galaxy in numbers we are only just beginning to count. For decades, they were nothing more than a theoretical idea, a ghost in the equations of astrophysics. Today, thanks to cutting-edge telescopes and decades of patient research, we are finally uncovering their secrets and rewriting the story of how stars, planets, and all cosmic matter comes to be. This is the untold story of brown dwarfs, the celestial misfits that never ignited, yet still shape the fabric of our Milky Way. To understand brown dwarfs, we first must go back to the birth of every star in the universe. All stars start their lives in vast clouds of gas and dust, cold, molecular nebulae, cold, dense clouds, mostly made of hydrogen and helium, the two lightest and most abundant elements in existence. Gravity is the silent architect here, pulling clumps of gas tighter and tighter together over millions of years. As a clump collapses, it heats up, spinning faster and forming a dense core at its center. For a true star, this process continues until the core reaches a critical temperature and pressure, about 10 million degrees Celsius. At that point, hydrogen atoms slam together so hard they fuse into helium, releasing an enormous burst of energy. This is hydrogen fusion, the process that powers every star, from our tiny red dwarfs to the massive blue giants that burn bright and die young. This fusion creates an outward pressure that balances the inward pull of gravity, and a star is born, stable, luminous, and destined to shine for millions or even trillions of years. But brown dwarfs never reach this critical moment. They are the cosmic almost stars, formed in the exact same way from the same gas clouds, but they never gather enough mass to spark hydrogen fusion in their cores. Imagine trying to light a campfire. You gather wood, stack it, and strike a match, but you never have enough kindling to keep the flame going. That is the fate of a brown dwarf. It collapses, it heats up, it comes so close to becoming a star, but it falls short. The exact mass line that separates a brown dwarf from a true star is one of the most precise numbers in astrophysics, 80 times the mass of Jupiter. Any object above this threshold will ignite hydrogen fusion and live as a star. Any object below it will never cross that line, doomed to be a brown dwarf forever. To put that in perspective, Jupiter itself is only 1/1000th the mass of our Sun, so even the heaviest brown dwarfs are still less than 8% of the Sun's mass. They are massive, but not massive enough. For years, scientists argued over whether these objects even existed. The idea of brown dwarfs was first proposed in the 1960s, but they were nearly impossible to detect. Unlike bright stars, brown dwarfs emit almost no visible light. They are cool, dim, and faint, radiating most of their energy in the infrared spectrum light that is invisible to the human eye. For decades, astronomers scanned the sky, looking for these dark objects, but they kept missing them. They were hidden in the glare of brighter stars, lost in the dust of nebulae, and too faint to register on older telescopes. It was not until 1995 that the first confirmed brown dwarf was discovered, a breakthrough that changed astrophysics forever. That object, named Tidé 1, was found in the Pleiades star cluster, and it proved once and for all that failed stars were real. Since that day, thousands of brown dwarfs have been catalogued, and we now know they are one of the most common types of objects in the Milky Way. Even though brown dwarfs cannot sustain hydrogen fusion, they are not completely cold and dead. They have a brief, faint moment of fusion life early in their existence. When a brown dwarf first forms, its core is hot enough to fuse deuterium, a heavy form of hydrogen, into helium. Deuterium fusion is a much weaker process than hydrogen fusion, and it only lasts for a few million years. Once the deuterium runs out, the brown dwarf has no more energy to burn. It slowly cools down over billions of years, fading into deeper and deeper darkness, growing colder and dimmer with every passing age. This short burst of deuterium fusion is what separates brown dwarfs from large gas giant planets like Jupiter. Planets never fuse any elements at all. They are just cold, inactive balls of gas and rock. Brown dwarfs, for a short time, act like tiny stars, making them a unique class of objects called substellar objects. Not quite stars, not quite planets, but something entirely in between. Astronomers have classified brown dwarfs into three main types, based on their temperature, color, and age: L dwarfs, T dwarfs, and Y dwarfs. L dwarfs are the youngest and warmest brown dwarfs, still glowing with a faint red or orange light from their recent deuterium fusion. T-dwarfs are cooler, appearing magenta or deep red, and they show strong signs of methane in their atmospheres, something no true star has. Y-dwarfs are the coldest and oldest, so faint, they are nearly invisible, with temperatures cooler than the surface of some planets. The coldest Y-dwarfs ever found have temperatures lower than the human body, making them some of the coldest stellar-like objects in the universe. These classifications help us map the life cycle of brown dwarfs, tracking how they cool and fade over billions of years, and they reveal just how diverse this hidden population really is. One of the most reliable ways to identify a brown dwarf is the lithium test, a simple but powerful tool used by astronomers for decades. True stars, even small red dwarfs, burn lithium in their cores within a few 100 million years of forming. Brown dwarfs, however, never get hot enough to destroy lithium, so the element remains in their atmospheres forever. When astronomers detect lithium in the spectrum of a dim substellar object, they know they have found a brown dwarf. This test has been used to confirm hundreds of brown dwarf discoveries, separating the failed stars from true stars and large planets with incredible accuracy. It is a small detail, but it is a key that unlocks the door to studying these elusive objects. Today, the James Webb Space Telescope, NASA's most powerful space observatory, is revolutionizing our study of brown dwarfs. Webb's infrared sensors are perfectly tuned to detect the faint heat and light of cool dim objects like brown dwarfs, even those hidden in the densest star-forming nebulae. Webb has captured detailed images of brown dwarf atmospheres, spotted clouds, and storms raging on their surfaces, and even found brown dwarfs orbiting other stars in binary systems. These observations are teaching us how brown dwarfs form alongside true stars, how their atmospheres evolve, and how common they are in every corner of the galaxy. Before Webb, we could only guess at the number of brown dwarfs in the Milky Way. Now we are finding that they may outnumber some types of true stars, making them a major part of our galaxy's population. The discovery of brown dwarfs has also forced us to rethink our definitions of stars and planets. For centuries, we drew a clear line between the two stars, burn fusion planets, orbit stars, and do not burn fusion. But brown dwarfs blur that line completely. They form like stars, not like planets, but they never become true stars. Some brown dwarfs float freely through space, not orbiting any star at all, while others orbit bright stars like giant planets. This chaos in classification has led astronomers to create a more nuanced view of cosmic objects, understanding that the universe is not divided into neat categories, but filled with a spectrum of worlds and stars and everything in between. Brown dwarfs teach us that nature does not follow our human-made rules. It creates a vast, messy, wonderful array of objects that challenge everything we think we know. Beyond their classification, brown dwarfs are also critical to our understanding of star formation. By studying how brown dwarfs fail to become stars, we learn about the exact conditions needed for a star to ignite. We learn about the minimum mass required for fusion, the way gas clouds collapse, and how gravity shapes every object in the universe. Brown dwarfs are like cosmic fossils, preserving the early conditions of star formation in a way that bright, active stars never can. They also help us study dark matter and the structure of the Milky Way, as their distribution across the galaxy can reveal hidden mass and gravitational forces that we cannot see directly. Even though they are faint and forgotten, brown dwarfs are powerful tools for unlocking the biggest mysteries of astrophysics. When you look up at the night sky now, you will still see the bright stars that have guided humanity for thousands of years. But remember, for every bright star you see, there are countless brown dwarfs drifting through the dark, the failed stars that never got their chance to shine. They are quiet, they are dim, and they are easy to ignore, but they are everywhere. They are proof that the universe is full of hidden stories, of objects that do not fit our expectations, and of mysteries waiting to be uncovered. Brown dwarfs remind us that there is far more to the cosmos than what meets the eye, that the most amazing discoveries often lie in the shadows, and that even the failed objects of the universe have a vital role to play in the grand story of space and time. As we continue to explore the Milky Way with new telescopes and new technology, we will find more brown dwarfs, learn more about their secrets, and deepen our understanding of how the universe works. These failed stars are not failures at all. They are unique, fascinating, and essential pieces of the cosmic puzzle. They are a reminder that in space, as in life, there is beauty and purpose in every kind of object, no matter how big or small, bright or dim. The universe is not just made of shining stars. It is made of all the things that almost were all the things that are different, and all the things that hide in the dark waiting for us to find them? Please like, comment, share, and subscribe to the channel.